Energy is everywhere, moving, vibrating, transferring from one place to another. But have you ever wondered how that energy actually travels through the world around us? The answer lies in one of the most fascinating concepts in physics: waves. Whether it's the ripple on a pond, the sound of a jet engine, or the tremor that shakes the ground during an earthquake, all are waves in action, transferring energy through matter without permanently moving it. In engineering, understanding waves is not a luxury, it's a necessity. Waves tell us how structures respond to sound, how signals move through materials, and how energy propagates in systems both natural and artificial. When a building trembles in an earthquake, when an aircraft wing flexes in turbulence, or when a communication signal travels through air, engineers are working with the language of waves. At their core, waves are simply disturbances that travel through a medium. They can be mechanical, like sound waves traveling through air or water waves across the ocean, or electromagnetic, like the light that allows us to see and communicate wirelessly. Engineers must understand both. For civil engineers, waves determine how structures interact with seismic vibrations. For mechanical and aerospace engineers, they define how materials respond to repeated stresses and vibrations. For electrical engineers, electromagnetic waves are the foundation of modern communication and signal processing. Every wave is characterized by key parameters: wavelength, frequency, amplitude, and speed. Together, they define how energy moves and how materials respond. When two waves interact, they can interfere constructively or destructively, amplifying or canceling each other out. This principle, known as superposition, forms the basis for technologies like noise cancellation and signal modulation. One of the most powerful ideas connected to waves is resonance, a concept you've already encountered. When the frequency of a wave matches the natural frequency of a system, energy transfer becomes extremely efficient. Engineers must use this wisely. Resonance can make an opera singer shatter glass, but it can also optimize the design of antennas, sensors, and musical instruments. From the gentle oscillations of a suspension bridge to the thunderous roar of a jet engine, wave physics governs how energy flows in every engineering system. It allows engineers to design safer buildings, quieter engines, and more efficient machines. It even extends to emerging technologies, from ultrasonic testing of materials to acoustic levitation and earthquake-resistant designs. In essence, waves reveal a deep truth about the physical world. Energy never stands still, it travels, transforms, and interacts. For engineers, mastering this language of motion is key to innovation. By understanding how energy travels through matter, we can design a world that not only withstands the forces of nature but uses them to create harmony, safety, and progress. This episode is part of the series Physics for Engineers: Foundations that Build the Future, an initiative of the Physical Sciences Consultorium, PSC, dedicated to bridging the gap between fundamental physics and real-world engineering. If you enjoyed this exploration, subscribe to PSC, explore more episodes in this series, and continue your journey into the fascinating world where physics builds the future.